All right, so let's then talk about some improvements we can make to the ideal model, because those ideal characteristics are not achievable. Okay, there's always going to be some non-zero input resistance, non-infinite input resistance Ri, and therefore there's going to be some input current In into the system here, right? So if you apply a voltage source here, if you apply some voltage to the system, there's going to be some current that's going to flow into the input of the amplifier, which is Rin. Okay. Now, similarly, how do you create a dependent voltage source? Well, you do it probably with transistors, but any dependent source cannot have a non-zero series resistance. Remember how we talked about any any real battery VS has an unavoidable series resistance RS. That's also true for any real dependent voltage source that you are going to develop. So, so that dependent source does have a non-zero output resistance RO. It turns out we can make it very small, but we cannot make it zero. And so notice also that then is this non-zero resistance is the Thevenin resistance that the load would see if you were to connect some load to this circuit. So the three parameters for a real amplifier are the gain A, the input resistance Ri, and the output resistance Ro. A is the open circuit amplification. So if we look at that, then, and this is V out right here. Okay, V out, or VO, if we wanted to write it that way, V out is equal to A times VI, right? That's fine, but that's only when the system is run open circuit, right? Meaning, what do we mean when it's open circuit? Think back to the Thevenin lesson we did last week. Open circuit meant like we are looking at the open circuit voltage. In other words, the port or the output of the system is not loaded. And here in this case, there is no load. As soon as we do connect a load, like this, that is now loading down the output. And in fact, what we're going to see is the output voltage, V out, the voltage delivered to the load, which is, it's the output of the amplifier. It's also, you know, V delivered to the load is equal to the output of the amplifier in this case. And what's going to happen is that it's going to get loaded down, right? The output V out is actually going to equal AVI times, just by voltage divider, RL, the load, over RO, the output resistance of the amplifier, times the load, right? This is just the voltage divider action that we've seen over and over and over again by this point in the course. And it's a very important part of the analysis for these amplifier blocks. Recall last time also that we were looking at Thevenin. Thevenizing a circuit helped us see how circuit blocks would behave when they interconnect. And I said that we would revisit that topic in chapter 5. That's what we're about to do on I believe the next slide. Yes, we are about to do this on the next slide. Okay, so again, the gain A is the open circuit voltage. Or rather, let me do that in red. It's the open circuit voltage. Open circuit, or in other words, also known as unloaded. there's no load connected to the output. All right, because once you do load, this would be the loaded output voltage. And what you can see is that you'll know that this term here, no matter what RL and RO plus RL is, this term is always going to be, hang on here, this term is always less than 1, right? So that always makes the loaded voltage V out less than the unloaded voltage. All right, so what we have now at this point, ignore the part that I drew in purple, the load there. The part just shown in black is the real amplifier model. And any amplifier you build, including op amps, operational amplifiers, behaves this way. So now let's take that, or you can model it this way, this real amplifier model. Now let's take the amplifier model, the schematic, and let's first connect a source to it. Let's connect a source R of some voltage source Vs. Oops, hang on here. Let's connect that, and then let's say that source has a source resistance Rs, right? It's unavoidable. Let's say it's a microphone, right? A microphone, yes, it generates a voltage, but it's got a coil of wire in there. And that coil of wire has non-zero resistance. You can't get away from it. It has series resistance. In fact, so does any source, including sensors, including other kind of transducers, things that convert energy from one kind into another. They all have, even the output of a preceding stage amplifier, if that has non-zero resistance. Everything has some kind of source resistance or resistance coming from it. Okay, and we apply that to the input there. We know that the voltage VI delivered to the input of the amplifier, keep in mind that the input voltage to the amplifier is the voltage across that input resistance, Ri. So how much input voltage is VI going to be equal to Vs? Maybe not, because there's going to be some current IN drawn into the input of the amplifier. If it were an ideal amplifier, in fact, where the input resistance was infinite, then there would be no current coming in, and you could say that VI was equal to Vs. But any real amplifier has non-infinite, even though it may be very high, it has non-infinite input impedance or resistance. And so you're going to get some current flowing across that Rs, which means you're going to get a little bit of voltage drop across it. And so, so then VI is, in fact, by voltage divider, it's the source voltage times Ri over Rs plus Ri. Right? Okay, so now we've seen that the input impedance or resistance of the amplifier loads down the source a little bit. It's loading down this voltage source right here a little bit. We'll talk about how much amplifiers load down sources and ways in which you can minimize that loading. All right, now let's go and take, we want to use the amplifier to its full extent. So we're connecting a voltage source, driving the input. And now the amplifier is producing some output voltage from that, right? So it's producing this V out here, like that, right? Now, V out would normally be the open circuit voltage would be equal to A times VI, right? Again, where VI is this piece right here. Now, it's not going to be open circuit because probably if we're using it as the amplifier, we probably want to connect the amplifier to some device. We want to transfer energy to something. If it was a microphone going into an amplifier and connecting to a speaker, we're going to want to send that signal to the speaker, and a speaker is going to have some non-zero resistance for 2, 4, 8, 16 ohms, something like that. So we'll go ahead and then connect that load now. I'll just draw it as a regular, just some kind of box. There's RL. And the voltage delivered, the voltage across RL, the output voltage, is going to be equal to, well, it's AVI times, right? Because that's how much voltage is generated here. That's how much voltage is generated here, right? This is AVI right here. But that's being loaded down by a voltage divider. So this is over RL, because we're going to get some non-zero current flowing through the resistor, right? This is I out. And so you're going to get a drop across the output resistance or output impedance, RO, and that's going to cause a voltage dividing action. All right. So now let's then go ahead and look at the entire expression for, what we really want to do is relate, we want to relate V out to VI. We want to see the total relation all the way from the chain, V out to VS. Sorry. We want to relate all the way through the circuit. So going all the way from the source voltage, VS, that's the source from some sensor or a transducer, something like that, an audio transducer like a microphone, all the way to the voltage V out delivered to some device. Okay, so what we're going to do is take this expression for VI and plug that into here. All right, so then what we can do is we can write V out as a function of VS. So this is A times, instead of VI, I'm going to put VS in here because it was VS times an RI over RS plus RI. Realize that this whole term here, right, this is just VI, right? And then we're going to put in the other voltage dividing action here, where this is RL over RO plus RL. Okay. Now, if we wanted to talk about the real gain of the system, so remember, A is the unloaded or open circuit gain. AR, this is the real gain. The actual gain of the system is always defined as the actual gain of the system is defined as the final output voltage V out divided by the initial input signal VS, not divided by VI, like that, right? That's VI is already going to be a little bit less than VS. So it's the ratio from the final output voltage to the input signal VS. Okay, so if we take that expression, the expression up here, and we divide that, the expression I wrote just above, and divide both sides by VS, what we get is that the real gain is equal to A times this term, RI over RS plus RI, times this term, RL over the load resistance over the output resistance plus the load resistance there. Okay, that's the total expression. The gain for the system, the real gain, is always going to be less than the actual gain, A. Do you agree? Look at these terms right here. This term right here, RI over RS plus RI, that is always going to be less than 1, right? It can't be greater than 1. This term here, RL over RO plus RL, that is always going to be less than 1. So the actual gain of the system is going to be the unloaded or open circuit gain, A, times two factors that can never be bigger than 1. So the real gain of the system is always going to be lower than the open circuit gain of the system, of the amplifier. And when I say system, I mean the whole thing connected, where you've connected an input source to the amplifier, and then that amplifier is now driving a load. Okay, so if that sounds reasonable, how then can we get the real or the actual system to behave like the ideal? In other words, how can we get the real gain to approximate the open circuit gain of the system? Which would be helpful, because that gain of the system, we could actually tune that, right? So you could tune that to be 10 volts per volt, or 30 volts per volt, or 200 volts per volt, or 2000 volts per volt. All right, how do we do that? Well, to do that, we want to make each one of these terms, like this one right here, we want to make that as close to 1 as possible. How do you do that? Well, you try to make the denominator, RS plus RI, you try to make it as equal to the numerator, RI, as possible. So that means that RS, the source resistance, has to be much, much smaller than RI, the input resistance. Now, the source resistance might be different from a lot of different sources. So one strategy to make this work, this amplifier work with lots of different sources, is to make this large. Make the input resistance super big. Okay? How about the other term over here, this one? We want that to be as close to 1 as possible. And by a similar account, that means we want the denominator of that expression to be as close to RL as possible. And to do that, that means making RO really small. So we need RO to be way, way smaller than the load resistance RL. Now, again, if you're designing an amplifier that's going to be working with a lot of different loads, what should you do? You want to try to make this resistance as small as possible. And in doing so, you'll make the amplifier behave like an ideal amplifier as close as possible.